Out of all the matrices in the universe, one tiny class behaves so beautifully that it earns its own theorem. A generic matrix can have complex eigenvalues and skewed eigenvectors that don't line up nicely. But flip the condition, make the matrix equal to its own transpose, and suddenly everything snaps into perfect right angles. A symmetric matrix satisfies A equals A transpose. The transpose flips entries across the main diagonal. The entry in row I, column J swaps with the entry in row J, column I. So being symmetric means every off-diagonal entry mirrors its partner across the diagonal. Look at this 3 by 3 matrix. The diagonal entries 2, 7, and 4 are free to be anything, but each off-diagonal pair is locked together. The 2, 3s match. The negative ones match, the 5s match. That single mirror condition is everything we need. Recall that any diagonalizable matrix factors as A equals S lambda S inverse. The columns of S are the eigenvectors of A. Lambda is the diagonal matrix whose entries are the eigenvalues, and S inverse is the matrix that undoes S. For a generic matrix, computing the inverse is real work. The eigenvectors might point in awkward, skewed directions, and they could even have complex entries. Symmetric matrices, remarkably, fix every one of these problems at once. Real symmetric matrices have two miraculous properties. First, every eigenvalue is real. No complex numbers ever appear. Second, the eigenvectors can be chosen orthonormal, mutually perpendicular and of unit length. Let's see this on a concrete 2 by 2 example. Take A with 3s on the diagonal and the 1s off the diagonal. The characteristic equation is the determinant of a minus lambda times the identity, which gives the quantity 3 minus lambda squared minus 1 equals 0. Expanding, we get lambda squared minus 6 lambda plus 8 equals 0. This factors as lambda minus 4 times lambda minus 2. So the eigenvalues are 4 and 2, both real as promised. Solving for the eigenvectors, we find 1, 1 for lambda equals 4, and 1, negative 1 for lambda equals 2, each scaled by 1 over the square root of 2, so they have unit lengths. Now take their dot product. 1 times 1 plus 1 times negative 1 equals 0. They are perpendicular. When the eigenvectors are orthonormal, we give the matrix a special name. We call it Q, and Q has a magical property. Q transpose times Q equals the identity matrix. Why is this true? Look at the entry in row I, column J of Q transpose Q. It is exactly the dot product of column I of Q with column J of Q. When I equals J, we are dotting a column with itself, and since the columns are unit vectors, the result is 1. When I is different from J, the columns are perpendicular, so the dot product is 0. 1s on the diagonal, 0s off the diagonal. That is the identity matrix. And here is the beautiful consequence. If Q transpose times Q equals the identity, then Q inverse equals Q transpose. The inverse comes for free. Now substitute Q in place of S in the diagonalization formula. Since Q inverse equals Q transpose, the formula simplifies beautifully into the spectral theorem. A equals Q times lambda times Q transpose. Let's assemble it for our running example. Q is 1 over square root of 2 times the matrix whose columns are 1, 1 and 1, negative 1. Lambda is the diagonal matrix with 4 and 2 on the diagonal. And because Q is symmetric here, Q transpose looks identical to Q. First, multiply Q times lambda. This scales the first column of Q by 4 and the second column by 2, giving 1 over square root of 2 times the matrix 4, 2 on top and 4, negative 2 on the bottom. Now multiply that result by Q transpose. The two factors of 1 over square root of 2 combine into 1/2, and the matrix product gives 1/2 times 6, 2, 2, 6, which simplifies to 3, 1, 1, 3. That is exactly A. Notice we never computed an inverse. We only took a transpose. Quick sanity check. Is QλQ transpose actually symmetric? Let's take its transpose and see what we get. Remember, the transpose of a product reverses the order and transposes each piece. So QλQ transpose, all transpose, becomes Q transpose transpose times lambda transpose times Q transpose. Now simplify each piece. Q transpose transpose is just Q. Lambda transpose equals lambda because diagonal matrices are their own transpose. And Q transpose stays Q transpose. Putting it back together, we get exactly Q lambda Q transpose, the same thing we started with. The factorization is self-consistent, symmetry in, symmetry out. There's a subtle word in our statement. Eigenvectors can be chosen orthonormal. Why can be? Consider the identity matrix. Every non-zero vector v satisfies I times y equals v. Every direction is an eigenvector with eigenvalue 1. There's no unique choice. We freely pick any orthonormal basis we like. More generally, when an eigenvalue repeats, an entire subspace of eigenvectors appears, and we choose perpendicular ones inside that subspace. When eigenvalues are all distinct, perpendicularity is automatic. Eigenvectors of different eigenvalues of a symmetric matrix must be orthogonal. No choice required. This theorem has a second name borrowed from physics, the principal axis theorem. The inertia tensor of a rigid body is a symmetric 3×3 matrix. Diagonalizing it finds the principal axis, the rotated coordinate system in which rotation decouples cleanly, with no cross terms mixing the axis. Same mass, different language. Whenever physics hands you a symmetric quantity, the spectral theorem gives you the natural axis for free. Now for the most beautiful consequence of the spectral theorem. When we multiply Q lambda Q transpose using the column times row rule, the result becomes a sum of simple pieces. We get lambda 1 times Q1 Q1 transpose plus lambda 2 times Q2 Q2 transpose and so on through lambda n times Qn Qn transpose. Each piece QK transpose is a rank 1 matrix. It's the projection onto the line through the eigenvector. So every symmetric matrix decomposes into perpendicular projections weighted by its eigenvalues. Let's see this for our example. A equals 4 times Q1 Q1 transpose plus 2 times Q2 Q2 transpose. The first projection, Q1 Q1 transpose, is the matrix with all entries 1/2. That's projection onto the 45-degree line. The second, Q2 Q2 transpose, has entries 1/2, -1/2, -1/2, 1/2, projection onto the perpendicular line at -45 degrees. Now scale, 4 times the first projection gives the matrix 2, 2, 2, 2. 2 times the second gives 1, -1, -1, 1. Add them together and we recover. A3, 1, 1, 3. The matrix has been rebuilt from its perpendicular projection pieces. So a symmetric matrix is, geometrically, just stretching along perpendicular axes, no rotation, no shear. Pure scaling in the right rotated frame. That single insight ripples outward. Principal component analysis diagonalizes the symmetric covariance matrix to find directions of maximum variance. Quadratic forms in optimization use the Hessian, which is symmetric. Quantum observables are symmetric or Hermitian operators, and their real eigenvalues are the measurable quantities. In mechanics, the inertia tensor is symmetric, and its eigenvectors are the principal axis of rotation. Whenever nature exhibits symmetry, the spectral theorem makes it computable. Real eigenvalues, perpendicular axes, and the projections that add up to the whole. The condition A equals A transpose looks small. The structure it unlocks is enormous.